It's an extreme pleasure and actually honor to be here. And I would like to thank you for your kindness and invitation. I was postponing this colloquium for a long time. But I'm extremely happy to be at the physics colloquium, because the story I will tell you is, and I'm a little bit afraid because there will be a movie afterwards when I say the story, and my jokes are not always appropriate, but this is a story, it's more or less correct. So the first time we invented vitrimers, on which I will talk, it was in 2011. And I was invited to Helsinki, to the university, by physics department to give the colloquium. And they wanted me to talk about the self-healing rubber, but because we had this new baby, which was Vitrimers, and I decided I will talk about the glass transition. And this was the most awful talk that I gave, because I have absolutely no perspective of what we did. And it was in November. The paper was published in November as well in Science. And it was one of the most disastrous talks that I gave. At the end, my colleague who invited me, he wanted to show that the soft matter is a physics. And the conclusion was maybe, but certainly not this one, okay? And so today is sort of a revenge that I will try to convince you that there is some physics and there is also a chemistry, and there are many interesting problems. So I will try to go very quickly through the things. We renewed completely our interest in the field, and I will try to give you the idea about the open questions at the end of my talk, and hope that we will have a chance to discuss. So thank you once again for the invitation, and it's great to be here. So now when I gave a formal introduction, I will take off my coat, and I promise you I will not go further in my striptease, and this is how it will stay. Okay, so the tradition of the school, which is nearby, is that it's physics, chemistry, maybe now also biology, and there were always trends to think about the applications. And the polymers were always present in the school. So the polymers are fantastic materials. They change completely the world in 20th century, and because they are light, they are easy to process, and they can use in very different applications. So for instance, the diapers here change the life of young fathers and mothers, and can completely change the life. And this was possible because people invented the super absorbent polymers, the polyelectrolytes, and when we use them, we don't realize how much physics theory, how much inventions goes beyond these objects. Pipes, all in all electronics was possible thanks to the dielectric properties of polymers. I have all adhesives are made of polymers, and these applications I like very much. So this car, funky car, is Twizy, and it has these windshields are made of plastic and not glass, and it's very impact resistant. And this was one of our it was based on our theory of self-assembling of polymers, and it's produced. It's a self-assembled nanostructured polymer and a very tough material. So knowing that I was at the origin, it's always, when I see these cars in Paris, I'm always very, very happy that they are funky. There is a lot of science which went into design of this process. Anyway, and so today, the story I will tell you is related to this. So glass is a hard but fragile material, but it has fantastic properties for the millenarians. And plastics, we talked about plastics. And now, the polymers are used in many, many applications, but nobody reasonable will make a champagne bottle from a polymer. You can make a bottle for Coca from a polymer, because if there is permeation of carbonic gas CO2 through the polymer, through the bottle, the soda is losing the gas, but you can live with it. But if you will have this with champagne, this will be awful. I mean, the whole France will protest. So we'll never put some champagne into a bottle, even if it's very, very heavy and complicated to transport and can break. On the other hand, so here is a glass made from polystyrene, which is a polymer, which again is glassy, is amorphous, like the silica from which, or silicate from which this bottle is made. So it is transparent as well, and it's much lighter. So we would like to make glassware from plastics, but again, nobody reasonable, it didn't develop. People wanted to develop glassware from plastics, but the reason why it didn't develop is that you cannot wash it. You cannot put a polystyrene glass into the dishwasher because it will become white and break. And if you look at your kitchen at the plastics glassware, you will find, or in the mixers and things like that with plastic parts, they are often become very beautiful and transparent at the beginning, but then they have plenty of small cracks and they become hazy and break. And so actually what happens is that when a polymer, a plastic, is in a contact with a liquid, in the case of polystyrene with a very important liquid, vodka, which is a mixture of alcohol and water, then it becomes very fragile because you have this cracking and cracks propagate. And in the experiments that we did in the lab, you take a sample of polystyrene, you put a small weight and put it in a solvent. When you take it out, it breaks very easily, and you put the stress of 30 megapascals, and after 2 minutes immersion in the alcohol, it breaks at this stress, and if you put at 30, for 30 minutes, it breaks even much, much easier. So again, you may think, okay, you cannot make a glassware from plastics, but actually, this phenomena, which is called of fragility in the presence of liquids, is called environmental stress cracking, and a quarter of failure in all applications of plastics come from this phenomena. And so this transparency was special for my talk, recent talk in US, and because this is a very serious problem. If you have a football game, you have impacts which are quite frequent, and they notice that these helmets break very easily, and they break very easily because the players put a sticker, and in a sticker was a little bit of solvent in the glue of the sticker, and they were losing their brains because this helmet became very fragile. So you believe me now that it's a very important problem. Now, I would like to tell you how to solve this problem. The problem, I do not understand what's the mechanism of stress cracking. So what makes the glassy polymers, the glassy organic materials, very fragile when they are in contact with not so good solvent? And I hope that in this room there is somebody who will solve this problem or would like to discuss with me. Anyway, we are ready. What we know is that if we cross-linked a polymer. So instead of having long chains, we make a network which is cross-linked. Then these cross-linked polymers, which are called thermosets, are very resistant to stress cracking. And actually, these were the first polymers. There were two categories of polymers. There are polymers which are cross-linked, which do not flow, cannot be processed once synthesized. And of course, they are insoluble because it's a network. So you can swell the network, but you cannot separate the molecules because they are covalently linked. And so when you prepare these objects, like the tire, you have to shape the object during the synthesis. And once you fixed the shape, you cannot remold it. By heating, it will not flow. It will, you cannot put it in a solution because, again, it will swell, but it will not flow. And this might be a problem. However, these materials are much more resistant and can be much more resistant. They have better mechanical resistance, chemical resistance, resistance to solvent, and they have a good dimensional stability. So for you who don't know, this is a telephone. And the first telephones, the telephone company was renting a telephone. So you were not a owner of a telephone. The telephone belonged to the phone company. Okay, so the phone company was making the telephones that will last forever. So they were making from the polymers, which is called bakelite, this black thing, and it was a cross-link thermoset, and it has much better mechanical resistance, scratch resistance. So the people will be very happy with the telephones. They will not break the telephone very often. And today, you may think, okay, we would like to change the telephone every week. So we make the telephones from thermoplastics, okay, which are polystyrene, which are not cross-link material, and it's the second category. And they are easy and to process, fast to process. They can be repaired and recycled because they are entangled polymers. They flow at high temperature, and they are soluble, so they can be also reprocessed by solvent or recycled by solvent, which is not the best way of doing it. And so for 100 years, because the polymers are for 100 years, there were two categories of polymers. There are these polymers which are thermosets, which were cross-linked, which do not flow. You shape it during the synthesis. You cannot repair it, but they have exquisite properties. And they were thermoplastics, which they had much less chemical, mechanical resistance, but they had the advantage of you can heat them, they flow like a liquid, you cool them, they become glassy or they crystallize, and you can give any shape you want and as fast as you want. And while the problem is also interesting, is that if the economy changes, and polymers always were important for developing new technologies. So if you believe people that the cars will be shared, if you believe, which means, and they will be maybe even electric, so then it means that you would like to have materials which will be like the telephone, because it will be rented. People will share objects, but then you would still like to, so you would like to have superior properties, but you cannot afford to have to go back to a very difficult processing, and you have to process them and you have to recycle them. And a chance is that there exists a third category of plastics, a new one, which was introduced in 2011 in our laboratory, and we called it Vitrimers. And this was done with my friend François Tournillac, and there were two very gifted PhD students, Damien Montarnal and Mathieu Caplot, who helped us in the first synthesis of vitrimers. And this new category of polymers is neither thermoplastic nor thermoset, and have both qualities, or maybe defects of each one. But it's a very different one. And so this is the story I will say. The only thing is there are many young people here in this room. So the only thing that I want to mention that neither Damien's nor Mathieu Caplot PhD subject was vitrimers. Okay? They accompanied us in this project, but the subject of their PhD thesis was completely different. And it's a good place to thank them for their openness, that they accepted to work on something which was not related to the things that they have to finish in 3 years, right? Anyway, okay. So the inspiration of vitrimers came from silica glass, from amorphous silica. And so if you take the glass, the archetype of glass, which is amorphous silica, made of silicates of amorphous silica on the basis, and you put it in a flame, so you can work it without controlling very well the temperature, and clearly it flows, it becomes malleable, and you can reshape it, and the silica, the glass, is not soluble. You can destroy glass, but you cannot dissolve it. On the other hand, if you take a polymer, like these American students did after they finished high school, so this is a polyethylene that they heated, and you can see it drips under flame. It drips because it becomes so liquid that it flows very easily. And actually, this was a problem this summer during the fire in London, and it was a tragic thing that the things were dripping in the building which was on the fire. So the fact that these two materials behave so differently is related to the different nature of the glass formation in these two systems. So if you take a polystyrene, you heat it, and you put it in an extruder, and you take it out, so it's very cold, very hot, and you put it into the air, so it cools down, and it becomes immediately a solid. So it becomes a solid glass, and the transition is extremely fast. So actually, when you cool the polystyrene, the viscosity changes dramatically over 10 orders of magnitude in a temperature range of maybe 30 degrees. And this is a very interesting behavior. It's completely non-Arrhenius. It's called Vogel-Fulcher law, or if in polymers it's called Williams-Landel-Ferry. But the essential thing here for us is that it is an extremely abrupt change. So that's why the polymer, when you heat it, the polymer drips, because the viscosity goes down. But the most important part is the system is amorphous, and because it's so viscous that when you apply the stress, it does not flow. Okay? Because the viscosity is so big that it doesn't flow, so it behaves like a solid. So for any purpose, the glass, which is a liquid, maybe, behaves like a solid. And the most, for all organic substances, this change is very abrupt. And because it's viscous, so everything depends on the time scale on which you looked, and everything depends on the history of your glass. So if you cool very fast, you do not, if you look at short time scale, the system behaves like a solid. But if you wait for 1,000 years, you will see that it flows. And so everything depends on the time scale at which you look at the system. And so with polystyrene, what you really quench, you quench the local motions of the polymers because you change a little bit the density of the system. So when you cool, the density increases, there is less free volume, and you basically quench the motions of some semi-local scale. However, silica does not behave the same way. So the glass does not behave like all these organic glasses. So all organic glasses, if you renormalize the glass transition temperature, they will behave the same because they will obey this non-Arrhenius law. Whereas the silica changes viscosity near the glass transition very, very smoothly, and the transition is not abrupt, and it obeys a simple Arrhenius law. And so for the physicist, the fact that something obeys an Arrhenius law, that it's a thermoactivated process, seems not very interesting. And so this was something that people really were most physicists were interested in this transition. However, the fact that silica is also insoluble and behaves in this very special way has a huge importance, of course, for processing, but it also has a fundamental importance to which I would like to underline and to discuss today. And it is important because if you look at most inorganic materials, and all organic materials have this abrupt transition, and only amorphous silica and maybe germanium oxide and some few other inorganic compounds have this transition. And it is called, for the reasons which are not very interesting, silica is called this behavior is called strong glass behavior, and this is fragile glass behavior. But important thing is that silica flows when it's heated, flows in a very special way, and is not soluble. And even today, there are papers which try to explain why the medieval glass, so this one I took this weekend in Chartres, this photograph, and does not really flow. So you can read that this is more thick at the bottom, and just because it flows. It's not true. This stained glass, which is more than 1,000 years old, in fact, does not flow. But the people already 1,000 years ago knew how to make the glass that it flows in a fragile way, in a non-Arrhenius way. And why I say it's very intriguing behavior, because if you look at silica, silica is a network. It's a covalent network. So it's like our polymer networks that we introduced at the beginning. There are silicium, silicon, and oxygen, and they are linked into a covalent disordered network. So this is a vision that the chemist will have. And of course, once you say it's a network, then it's obvious that it's not soluble, unless you break the bonds, which you can do chemically with a very strong acid. But then the question is why it flows. And when you look at these papers about which are published even this year, about how the stained glasses are made and how the glasses are made and what is the transition, then you find that people say something and then they say, oh, but probably you break the bonds. But the silicium-oxygen bond is extremely strong. The energy of the bond is 800 kilojoules per mole. So if our mathematics is correct, at 2000 degrees, the thermal energy is only 18 or maybe 20 kilojoules per mole, which means that the probability of breaking the bond is non-existing. You cannot break the bonds by heating of silica by heating to 2000 degrees. So the question is, what makes the system flow. And of course, then people say, oh, but they are impurities. We have silicates, so they are alkali atoms, they are boron, aluminum, and so on. And so this makes the system, the bond somehow less robust or something like that. And so I will argue that the impurities are important, but they are not important for breaking bonds necessarily, or for going closer to the percolation threshold of this network, but they play a role in the kinetics of this system. But before I do it, and this is not how, we didn't want to say that we know how silica works at that time, but now today I will say that yes, I think that we know. But we were less ambitious. We said, since there's no substance in this world which behaves like silica, except the silica, there's no organic materials that behave as silica, can we design the organic material which will be able to flow at high temperatures, and yet at high temperatures it will be not soluble. So is it possible to have a network which can flow, but which will be permanent, with permanent bonds that they will flow? Okay? And once I explain it to you, then everything will be easy. So of course I have to have some help to explain. So I need 4 volunteers to show you how it works. So maybe you, and you. Okay? Please come. Don't worry. It will be just like dancing. And I need the fourth person. Okay. So I will show you. Wait to the end. So the very important point is a catalyst. So I will be a catalyst, and I will tell you what is the chemistry doing, okay? So this will be dynamic covalent chemistry. So please, so here you make a bond. So I will show you how you can make how you can make a network, but this will be a mini network, of course, in which the number of bonds will stay the same. They will be never broken. And yet we will change the topology of the network, which means that we will be able to diffuse and flow. Okay? And so the idea, so the first reaction is a normal, which is called the exchange reaction. And so you will come here because it's easy to distinguish between something. So you see they are very, very stressed because there is a lot of tension because they don't know what will happen. Okay? And the best way to relax the tension, the stress, is to change a partner. Okay, so we will change the partner without changing the number of bonds. Okay, so the catalyst was very fast, and now you see the number of bonds is exactly the same. It's still 1. However, you are able to diffuse and relax, change alike, and it is relaxed. Okay, so this is called an exchange reaction. So you can see that by using these exchange reactions, I'm able to change the topology at the same time without changing the number of bonds, because we just come for a short time together and then we exchange the partners. Okay? Now, so this is one reaction. The other reaction, so please come, is much more interesting, and I never showed it. Okay? So it will be more difficult. So please make a bond, and please make a bond. And this is called the metathesis reaction. Okay? So metathesis is that they come together, and then you go together, and you go together, and then we never, ever break the bonds, and yet we change the partners, and we change the topology of the networks. There is a different possibility, okay, which is very important for another metathesis reaction. So please give 2 hands. So this is my new stuff, okay? So, and then I'm a catalyst. You break slowly this bond, but you are still always together, and then you come, then you break this bond, and this bond, and then you come together, and you come together, and then again the number of bonds is the same without ever changing, breaking the topology. So and the two types of reactions exist in chemistry, and this is called metathesis reaction. Okay, thank you so much. Now you can upload that. Okay. Okay, so once we, so this is more schematically drawn. It's again the same. I will go immediately to the principle of the network. So in the network, we do exactly the same. We have a network. these two things come together and they change the topology. So you see this part of the network can diffuse and can relax the stress, and this one changes. So in other words, I have a covalent permanent network which undergoes exchange reactions. So the number of bonds remains constant, but the network topology fluctuates. And if the network topology fluctuates, I can diffuse and I can relax the stresses, which means that I can flow. Yes?
What is the dynamics which drives this?
Okay, so here it is. Okay, so if these reactions are the thermoactivated reactions, okay, and they are catalyzed or not catalyzed, it depends on the chemistry. So if these reactions, so it's just going through the barrier, you know, coming together and how they change, okay, and they will be thermoactivated. So if these reactions at high temperature are very fast, then the material is a liquid, okay? Because it's just a network which changes all the time the topology. But if a reaction takes 1,000 years to occur, then for 1,000 years the system will not flow. And so if the reaction is thermoactivated, this means that the system will change the relaxation time by a simple Arrhenius law. Okay? And so the first reactions that we used is transesterification, which is used all the time in the industry. You take alkylate, you take an ester, you make, instead of just being like we were, you make a pyramid, and then you exchange the radicals here. It's exactly what we did in it. And the chemistry we use, so this is Mathieu Caplot, which makes, we knew in the lab, we knew the epoxy chemistry, and instead of doing it with amine, we did it with acid or anhydrides. We added just the transesterification catalyst, which makes this reaction rapid at the conditions we wanted, which is maybe 200 degrees or something like that. And then we obtain a vitrimer. And so as you can see, the chemistry is extremely complicated because it's like it's epoxy, but you can make it a 200 grams scale very easily. And what you get is something which behaves like a rubber because it's a cross-linked polymer. It's elastic. It becomes birefringent if you pull at it. Yet if you put it in a solvent, in a good solvent, which is trichlorobenzene here, at 180 degrees for 16 hours in this experiment, you can put it for weeks, and it will swell, but it will not dissolve. And yet when you heat it to 150 degrees and you put a stress, then you see that it deforms, it flows, and uses a shape. So it's malleable, and you can calculate the viscosity. And then when you plot the viscosity as a logarithm of viscosity as a function of 1 over temperature in this Arrhenius plot, you find that the vitrimers behave, the epoxy vitrimers and the other vitrimers which we made since then, behave just like silica. They obey this law, this Arrhenius law, and they behave very differently than all other plastics. So clearly vitrimers are a new class of organic materials which combine this aptitude to flow and be insoluble. And in order to put this concept forward, we said that we can have a glass transition not by changing the density of the system, but by changing by freezing the topology of the network. So rather than having, you know, a network it has a topology which fluctuates without the fluctuation of the number of links and functionality of the network. And so this is a new idea, and it's like silica. Now in terms of polymers, we had thermoplastic thermosets, and now we have vitrimers, which again, they flow and are insoluble. Okay, so it's a new category of polymers and plastic as well. So once we did it, and this is what we will play now, we can do the same things. And what we did the same things that glass workers do. So we took a rubber, a vitrimer, rubbery like vitrimer, a band. We deform it to a helical shape. So then the stresses, when you do this in a rubber, you build up the stresses, right? And normally the rubber will come back to this shape again. But if we heat it with, not with hair dryer, but we just heat it with under nitrogen so they don't oxidize for 2 minutes, we will relax the stresses, and so here we deform it. The stress is built up, so you see it becomes birefringent, and then you cannot hear it, but we put this nitrogen blower, hot nitrogen blower, and the stresses relax, so the birefringence disappears. And then at the end, what we get is a new shape, which we obtained without mold, without anything. And if we put a weight on it, it deforms like an elastomer. And then we relax it, and it becomes. So we can make, so we can reshape it without a mold, like a glass blower reshapes a glass. We can also repair it and recycle, because if you take two vitrimers, so they have defects at the surface. But if we put it together and we heat it, then we have exchange reactions across the interface, and it becomes just a one bulk material because the defects diffuse into the bulk of the material. So you get a perfect adhesion, which means that, so this will be a hard epoxy vitrimer. So you have a hard plastic, you grind it, it's a cross-linked insoluble plastic, you grind it, you heat it in a mold, and you get exactly the same, or almost the same properties as you had at the beginning. Because this little powder, you can make adhesion in this powder. Okay? So you can recycle and reshape the thermoset like a permanently cross-linked insoluble materials. And so then we can, so because some like it hard, so we also show that we can make composites. And again, with the composites, so there are plenty of glass fibers, and so this is important if you want to make light planes, light materials. So you have the resistance of typical thermoset, the modulus of typical thermoset, and then you can assemble it just by heating and adhesion. And so this was in 2011, more or less. And since then, there are plenty of vitrimers which have been synthesized, and it has been shown that there are interesting plastics and elastomers which are vitrimers. The composites were made. There are also some functional materials, and this one I like very much. It's a liquid crystalline polymer in which you can completely simplify the processing. It was done by Terenchev and his Chinese collaborators from University of Beijing, and in which you can organize this liquid crystal by deformation without, and still being a network being cross-linked. And so this can completely change the way the liquid crystal actuators or lasers can be done, and it's interesting physics related to this as well. Or you can make shape memory materials. You take a chair like this, you heat it and you make it flat, and then when you heat it back, you don't relax completely the stresses, and when you heat back, it becomes a chair. And there were plenty of chemistries. There were polyesters and epoxies, the ones that we used first, and polydienes, polyurethanes, polyimines, and so on and so on. And at this point, and it's like there are a lot of efforts and many papers which are done on vitrimers with chemistry. But none of these chemistries could make polymers from the monomers, from the materials that were used as polymers mostly. What I mean is that all these chemistries which were developed had always the heteroatoms in the backbone. And you know that most organic compounds, it's carbon, 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 carbon and hydrogen. So the most polymers which are produced are polyolefins, polypropylene, polyethylene, maybe polystyrene. There are acrylics here in others. And so this was the first challenge, how to make the polymers from the monomers of interest. And the second challenge was how to make it by using the same tools, how to make them that they, when heated, they flow as easily as a normal thermoplastic, so we can make objects with the same speed and using the same tools as they made done today from the vitrimers. And we solved this problem. This paper was published in April in Science, and the work was conducted with Renaud Nicolai, young professor of chemistry in our laboratory. And basically what we discovered is the metathesis reaction, which I showed you, but of boronic esters. And using this chemistry, we could respond to these two challenges. So the first question, why boron? Why boronic esters? So the answer is, one of the answers is that when I was, so this is my driving license, okay? And I'm not very easy to recognize, but roughly when I was this age, we made a self-healing hydrogens with the using borate, but we didn't call it self-healing at that time, which was very bad. But we knew that boron-boronic esters can make very rapid, so we can make supramolecular chemistry with this. But more seriously, boronic esters are they make an extremely strong bond, and they are very tolerant to many chemical groups, anhydride, epoxies, acrylates, and esters. And so they are very stable chemically, and they are very stable thermally. And the idea here is that if we take these two boronic esters and we mix them together, they will make 4 boronic esters by scrambling this acid and the diols parts without breaking together. And so Max Redger, who was a student with Renaud, he synthesized extremely pure boronic esters. He worked in very anhydrous conditions, so not to hydrolyze these units. And when he mixed them at 60 degrees, and he made gas chromatography and mass spectroscopy behind, and it was gas chromatography, sorry. And he found that he starts with 2 esters and he finishes with 4 esters, so they scrambled the diol and boron part, and the reaction is very fast. So in other words, we had this metathesis reaction as in this dancing experiment that we had here. And this metathesis reaction didn't require any adding of any catalyst, and it was depending on temperature. So with this, it was possible to design the systems, to take the systems, the normal polymers, and modify them to incorporate this boronic ester. And then we could, so for instance, we could copolymerize monomers which have this boronic ester groups, and then we could cross-link them by this metathesis reaction. But at the same time, the metathesis reaction was giving at high temperatures these exchange reactions which enable the system to flow. And so, for instance, we made a plexiglass, a transparent polymer, and with polymethyl methacrylate, which we could adjust viscosity, and it was completely cross-linked, but so it was not soluble at all. But we could manage to have a very high, very low viscosity at high temperature. And there are many parameters that can be adjusted in the system, because you can adjust the number of grafted groups, you can adjust the number of crosslinks, and so you can make the system, you can choose the properties you want, you know, how fast you could process, and compromise with degree of crosslinking you have. And the idea is that you can inject mold the system, or you can compression mold. And this sample is interesting because it was grinded 5 times and reprocessed 5 times. It has the same properties, mechanical properties, but it stays transparent and doesn't become yellow. So these materials are interesting. So we can do the same thing with polystyrene. And if we do this stress cracking resistance experiment with which I started my talk, then the vitrimer resists very well to the alcohol. So it will not fracture under the stress, and it can be processed, injection molded, it can be compression molded, and it can be recycled many, many times, and it still has this exceptional solvent resistance. And we can do also differently. We can buy a polymer, in this case it's polyethylene, and then we make a reactive ester. We graft in the melt the system, and again we use the metathesis to make a network and the metathesis to relax the stresses, and this modified polymer flows, and it has better mechanical resistance, a better improved chemical resistance, and it behaves like a cross-linked polymer, yet it is recyclable and reflowable. So, and with this I will almost finish. I would like to talk about applications. So what I believe is that it's maybe not, that pretty soon we'll have the applications which could change many, many things. In particular, in electronics, there is a problem of how you, of soldering. You would like to solder without, at high temperature in order to not use toxic compounds. The problem is that you have to protect your electronic parts in plastic cases which has a good electric properties, and polybutyl terephthalate is, for instance, one of these plastics. And what we have what Francois and his student André de Mangeon have shown is that we can make a vitrimer, and this vitrimer enables to make electronic connectors, and this should, we hope very, very soon, it's almost on industrial scale now, it should completely change the way the electronic components are produced, and in particular eliminate very toxic metals which are used in it, because we can go to higher temperature without these things collapsing because they have. Adhesion is again very interesting because we can control, and in particular we can make adhesion of very compatible polymers, because first we put polar groups which go into the surface, and then we have the reaction across the interface. So plexiglass, PMMA, and polyethylene are completely incompatible. There's absolutely no way to make adhesion of them. But if we introduce these boronic esters, we can get a very strong adhesion. We can even in some classical tests, we can even break PMMA and something. And so why it's interesting? It's interesting because if you look about how the plastics developed, so they double the number of plastics every 13 years. And so which means that every 13 years you go like this on this curve, because basically economy of the world increases. But at the same time, if you look at the steel, you don't economy develops, but the quantity of steel basically stays constant. And the difference is that steel is reused and recycled, and plastics are not reused and recycled. So there are basically two problems. There are many problems of with recycling of polymers and plastics. But one is that, as I said, long chains have very low entropy of mixing. So this means that I cannot take two polymers, mix them together, and make something of them. So I have to sort them and incompatible polymers. So this is one problem. And the second problem is that if it's cross-linked, we said it cannot be reprocessed. And so the idea here could be that if we add these grafting groups into the system, then the polymers will be incompatible, but we can control the interfaces and adhesion between these polymers. So it could be that we could make a very high performance material out of by reusing plastics with the better properties. Okay. So this is my last comment, because I'm tired, but you are even more tired probably of hearing to me. But so now I come back to the question of a glass. So the question is the glass a vitrimer? Okay? So do we have exchange reactions? We change the topology of the network, of this covalent network, and make it flow at high temperature and be areneous. And the idea that we had is that the impurities, the things that are in silicates, act as catalysts to make these exchange reactions possible. We were talking about it, but then Dominique Mascher pointed out to me that geologists actually were studying the silica, amorphous silica doped with the sodium silicates, and doing NMR at very, very high temperatures, because the magma is a glass that flows at high temperatures. And what they found by this NMR, the scheme that they put forward is exactly the same scheme that I made by this dancing experiment and by this. So basically, thanks to this non-bridging, what they call non-bridging sodium, which acts as a catalyst and which facilitates the exchange reaction through this intermediate state in which the silica have more neighbors. So we are trying, and this is one of the open questions, we are trying to make sense now of the phase diagrams of and see why different silicates behave differently, and to look at this not in a static way, how the changing the network connectivity by putting some non-bridging atoms, or maybe higher function, putting things which have higher functionality like boron, but maybe this boron just enables the exchange reactions in silica. So with this I will finish, but I cannot finish without thanking the people who really contributed to this, who accompanied this whole adventure. So I mentioned during my talk Renan, François, Damien and Mathieu, and Max Redre, and we were joined in this new part with the boron atoms by two postdocs, Tristan Domenac and Rob van der Wegen, and Antoine Briac is making a thesis, continues this work with Renan on boronic esters. And with this, I would like to thank you very much for your attention.
Well, I'm not sure I have fully understood the catalyst. So the catalyst is what makes a polymer, not connected polymer chains that makes it into a vitrimer, and it gives some energy barrier to the change of connections. Is that it, or I have completely not understood?
No, so the catalyst is not necessary. If the catalyst is not really necessary, for instance, this boronic is not necessary. The catalyst just controls how much in the I need to make these reactions occurring at the right temperature range. So by making catalyst, which indeed changes the barriers for these exchanges or puts the partners together, I can make faster or slower in the range of temperature that I have. But the principle is always the same, that for some, so in terms of chemistry, for some time, they come together, they make a complex together, and then they change the partner. So let me, I don't want you. So I will go to the transesterification reaction. So take this reaction, transesterification, okay? So we have alkylate here, which comes in here. It polarizes this link, okay? So it makes sort of, for very short time, it makes a complex, make an intermediate complex, an intermediate state, and then this electron goes to this electron, and you just, instead of this one going back to this position, which can happen, it's this one which goes out, and the R2 stays together. Okay. So in order to, so if you make this link weaker with the alkali metal, or you attack this ester, you make a complex we use zinc, so two esters will be weakened by a zinc here. You make this reaction easier to occur. Okay, but it's just bringing. I mean, it's essential, but it's not, a formal condition to have it. So in the boronic esters, what we think happens in this metathesis is that these two esters come head to tail this way, and they make a complex again, and there is a peeling. Anyway, I mean, there's a mechanism in which we can have the acid and we can have exchange of this one, which is absolutely not clear and not sure what it is. But so that's why I will say. But in all exchange reactions which have been invented, there is one which I didn't show with vinyl logos. In each time you have to activate something that it exchanges. And imine has apparently imine, I mean there are many exchange, and now more and more are discovered and more are studied because of this context of Vitrimers.
When you want to change the energy barrier, you change catalyst or you change its concentration of catalyst?
Both. You can do both. So, for instance, it's a very good question. So, if you change the concentration of catalyst, increase the concentration, the things become faster because you have more events which can occur. And if you change the catalyst, you have more efficient catalyst, it will again be faster. The problem is that if you want to make a rubber, so because what you don't want to do is when you heat the system will be deformed permanently, and so it's always a problem between the service temperature and the temperature you look. Okay, so then you would like to have a chemistry in which you can block the catalyst again and block the reactions again, and then you can think about different triggers. You can think about light, but then the material has to be transparent. You can think about pH. And so by changing pH, your catalyst becomes non-active or active. And so all this is sort of open again, but you are right.
Does it help if you put boron in a standard glass, I mean silica glass, Or is it incompatible with what
So,
you told?
I think if in my next life you invite me, I will have an answer, but a proper answer. But yes, yes, the borosilicates have a very special properties. They are indeed more fluid or some, indeed. Okay. Now, how it's going on, I don't know. I mean, this is again something that I would like to understand. But yes, boron is used in glass industry very much so. Probably for the same reason, because it has an orbital which is sort of missing, empty. Louis?
I have a small question. Vitrimers, so they seem to be very robust against a lot of attacks from chemistry or temperature. Is it true, or are they sensitive to several, I don't know?
No, okay, no, it's actually, so actually, again, it's an excellent question. So because we have to be very, very clear about it, okay? So when we had the referee of this paper, when we said, oh, these are, they don't change, he said, look, your color changed, okay? So clearly there is some oxidation, in this epoxy is oxidation. The epoxy chemistry, this one is extremely robust in the sense that we can do it, reprocess many, many times, and but the robustness in many chemistries which are described in the literature, there is a problem. And this is a very good question, because why is this, we are so excited about the boronic esters? Because if I want to extrude my polymer, and if I have a secondary reactions, which means so I heat this polymer to 200 degrees, and then I have a secondary reactions which will make permanent crosslinks. So instead, I don't know, I use transesterification and I make ethers rather than esters, okay? So then I will have a permanent crosslink which I make, and it's sufficient to have one crosslink per chain. So if the chain has 1,000 monomers, so 1 in 1,000 of secondary reaction will block the extruder. And when people look in organic chemistry of small molecules, and if they have a yield of 80% or 70%, they say, oh, it's nice, right? Or maybe not so nice, but it's okay. But here, if I don't have, if I have only 1 per 1,000 of secondary reactions which make a permanent link during this process, so if this was not just the oxidation which didn't lead to this, then I will get, indeed I will have insoluble something which is not. So in the literature, and in it, it's always a question, so the question you ask is always a question that has to be asked, how robust is the chemistry behind? In the boronic esters, again, we don't have much, it's very new. But the question you can ask is what will be when what will happen if there is hydrolysis, how, if you want to use it in pipes for hot water, what it will be. But even from fundamental questions, you know, how you control, from a point of view, it's an important question. Yes, so it's a problem. It may be a problem, but sometimes that's our chemistry at the beginning was very robust.
Okay. So thank you very much, Professor Leibler, for this excellent talk.